right, remember the overall schematic of our system that we're analyzing. I gave you that first time. We have an upper reservoir with elevation H and a lower reservoir at the bottom. So those are your two reference points for Bernoulli's equation. If we take a look at the Bernoulli's equation again, go ahead and you apply your free surface assumptions. So you're going to get rid of all these terms. Z2 is basically 0. So you get rid of that term as well. Take a look at what's left. Your input elevation, H, Z1, all your major losses, all your minor losses, your turbine head that you're removing, that's all got to be 0 at the end. So remember what I told you about this problem is that it is a class 2 problem. You don't know what the volumetric flow rate is. Now in part 2, I gave you the answer for a specific value of H so that you can check you have everything set up correctly. In general, for an arbitrary value of this elevation H, you're not going to know what Q is. So how do you check it? Check that value. Check the sum of everything. What you need to actually go through in part 3 is for a given elevation, you have to guess what Q is. And then everything else is computed from that. No, you cannot explicitly solve for the velocity. I know several people have been attempting to do that. You can't do it. It's an iterative problem. Everything is dependent on the velocity. Friction factor is dependent on velocity. And that's the main thing. So all of your major and minor losses, go ahead and compute those for the given Q that you assume. And then add up all these terms. If it does not add to 0, adjust your value of Q. And then it will propagate all of your equations. All of your formulas, it will update all of these terms automatically. And then you can get closer and closer to 0. Yes?
Why is B2 0?
It's a free surface. The lower reservoir is a free surface.
Oh, it's not allowed to suspend over, it just goes right onto the surface or...
That's the easiest way to do it.
All right.
What is, why is there a separate term HT from HL major and HL minor?
All right, this is your major loss, right?
Right.
Friction factor, L over D, velocity vector. These are all your minor losses, right? All your K sub L's, velocity vector. This is the work from the turbine. Now again, in part 4, I'm explicitly giving you a value to use. Excuse me, in part 3, I'm explicitly giving you a value to use.
Okay.
That I know works with this value of Q that I've given you. So you can get everything to sync up. In general, for the final analysis, when you are changing Z, remember this is going to change. Then the Q and the W dot will not be consistent with each other. So that's why we're looking at the turbine model separately in part 4. So in part 3, I'm giving you a very specific value for H, a very specific value for Q, a very specific value for W dot. And make sure you get all that to work properly. So the idea, again, is we start from for a given H, what you will do is guess the value for Q. You will compute your velocity through the system at various points. You will compute, everything that's dependent on velocity. Friction factor, Reynolds number, everything else. All right, and then finally at the end, check the sum of terms. Which is basically check all these terms in Bernoulli's equation. They better add to 0. If it's not adding to 0, adjust your guess. All right, in part 4, let's see if I can talk about that a little bit. I'll leave this on the board. Part 4, I give you very explicit instructions, which will hopefully answer a lot of the questions, but nevertheless, we'll go over that again. I give you an explicit